Hmm.
Up next, we have Eileen Yingst talking about the Heimdall camera system.
This is Eileen with Soundcheck.
We can hear you, Eileen.
Great, thank you. So I'm very pleased to be here. I am the principal investigator for the Heimdall camera system, and I would like to go to the next slide, please. I am honored to helm this ship of most excellent team members. I'd like to especially point out your co-chair here, Ryan Watkins, and I would like to also point out that Heimdall is a name, it's not an acronym, just so you're aware. Next slide, please. Heimdall is a 4 CMOS camera system, RGB cameras, plus a DVR, a digital video recorder. It will be flying on one of the CLIPS landers meant to launch in December of 2022. The 4 cameras are approximately 80 by 60 degrees field of view. The descent imager, or affectionately known as Heidi, is a camera pointing straight down to image the landing plume. It will get 500 microns per pixel on the surface and, of course, coarser resolution depending on its altitude. It's a panoramic imager that is designed to map geologic context at 5 millimeters per pixel at a distance of 10 meters. That improves, obviously, as you get closer to the imager. Regulus imager will yield high-resolution imaging of, not surprisingly, the Regolith at about 35 microns per pixel. And then there's a workspace imager as well, and that's meant to document the activities of other instruments, including the sampler arm. The arm is courtesy of Maxar, the folks who brought you the MER IDD, that is the arms that were operational on Spirit and Opportunity. So the panoramic and the Regulus imagers are mounted on that arm. The descent imager and the workspace imager are mounted on the spacecraft body. Next slide, please. So we were asked to provide a couple of top questions for the lunar surface, and these, not surprisingly, dovetail into our science objectives. Firstly, how does the lunar regolith behave during human-induced interaction? And this means anything from, as you've already heard, plume regolith interaction during the descent and landing, to an astronaut dragging her gloved hand through the regolith as she's on the surface, to instruments being deployed on that surface, to, say, a scoop that's scooping up samples of the surface. And the second question, how can we navigate efficiently remotely on the lunar surface? So we have experience doing that on Mars, and actually to a lesser extent on the Moon, but we need to be able to understand the terrain that we are driving through. If we're going to have a semi-autonomous or autonomous rover, we need to be able to navigate autonomously, and that means having a very clear 3D understanding of the surface that we're driving on. Next slide, please. The science objectives for Heimdall: we intend to characterize and map the landing site at multiple scales to give us geologic context. We intend to record and model interaction between the regolith and the landing plume, to characterize that regolith, and to provide that ground truth to support autonomous navigation software for future landing. Next slide, please. Has the next slide been advanced? Oh, great. So going through each of these science objectives very, very briefly, the 3 images that you're seeing on the bottom here represent the types of images that we would expect from the camera system. You can see where it says 1 and 2, those are all the same boulders, 1 and 2, just at different perspectives and different resolutions. So on the left, you have an image from the LROC camera. That's an image that you might get from orbit. On the right is the type of image you might get from the descent imager from Heidi. And then in the middle, those are in situ images that you would expect to get from something like Heimdall's panoramic imager. You can see that if you accordion all those together, you get a much more nuanced idea of what the geology looks like, and therefore a much better idea of how to interpret that geology. Next slide, please. Heimdall is also designed to help characterize plume landing regolith interactions. And you've heard a lot about that already. I'm just going to add the fact that one of the things that is really of interest to us is being able to get a quantitative assessment of what's going on as the spacecraft is landing. As you've already heard, some of our best data is from the Apollo era, and in some cases, the best data that we have is freeze frames of videos that have to be coupled with the recording of the astronauts calling out altitudes. And that's the best data that we have. So one of the things we're really hoping to be able to do is to quantify a lot of that data to fill in plume models much better. Next slide, please.
4 minutes.
Thank you. We want to be able to understand the characterization of the regolith. The regolith, as you've already heard, is the product of a complex set of mechanisms. You've got endogenic, you've got exogenic, you've got impact melt, all laterally and vertically mixed. So what we want to do is to be able to resolve the larger fraction, size fraction of the regolith grains. So in these images, you can see on the left an actual example of lunar regolith, and then on the right, this is actually a Martian soil fragment. It's 30 millimeters long, but this gives you the idea of the resolution that we'd be talking about with Heimdall. So the idea is to be able to look at size distribution, particle shape, cohesion, slope stability, and maybe even trafficability. And the cool thing is that the regolith imager will be able to give you complementary data to the descent imager, so you can pin those two together. Next slide, please. So in summary, for the two questions that we feel are some of the top questions about the lunar surface, Heimdall will be able to address both of those questions. The descent imager is going to give us images of the plume-regolith interaction that will give us digital quantitative information specifically designed to feed into plume modeling. The regolith imager will give us images of the soil, potentially undisturbed depending on how much activity we get from the landing plume, but at least because it's mounted on the arm, it will allow us to kind of choose where we want to be able to take those images so that we can tie it to what we've seen in the descent imager. And then the workspace imager is going to be able to document the interaction between the surface and the sampler instrument and any other instruments that might come through that workspace. In terms of navigating efficiently, the panoramic imager will allow us to get stereo images translated through the arm, as you heard actually occurred with InSight. We'll be able to do that here. We'll be able to translate the arm from image to image so that we can get stereo images of the surface so that we can feed those into autonomous navigation software that's being developed for future missions. That's all I have. I'd be happy to take questions or return my time as needed.